Section 7.4, the distribution of the sample mean x bar. So we ended the last section saying that we needed to know under what conditions x bar was normally distributed, and in this chapter we're going to give two theorems that state what those conditions are. The first one is Theorem 7.4, and it says that if the population we're sampling from is normally distributed with a mean of mu and a standard deviation of sigma, then for any given sample size, x bar will also be normally distributed with mean mu of x bar equals mu and a standard deviation sigma x bar equals sigma over root n. So if the population we are sampling from is normally distributed with a mean of mu and a standard deviation of sigma, then for any given sample size, x bar will also be normally distributed. And then this part is just a repetition of our previous theorem, which tells us the values of mu of x bar and sigma x bar. So the new piece is this one. If the population is normal, then the x bar will be normal also. So that's our first condition. If we know that the population is normal, then we'll know x bar is normal too. And this means that probabilities for x bar can be found using areas under a normal curve. It's always important to know if your x bar or your p hat is normal, because to do probabilities you want to be able to use area under a normal curve. It's a nice easy way to get probability. So let's look at an example to see how the mechanics of this work. Suppose that a random sample is going to be taken from a population that's normal with a mean of 195 and a standard deviation of 31.52. They're saying this is a population mean, so that's mu. And they're saying this is a population standard deviation, so that's sigma. And then they're saying for a sample of size 24, so that's n equals 24, what is the distribution of all possible sample means? So the first thing is translation. They're asking us what is the distribution, which is a question about shape, and they're asking that about the sample means, and the symbol for a sample mean is x bar. So they're basically saying what shape are we going to get for x bar. And what I can say on this is that x bar is normally distributed, and that's the shape that I'm always hoping for my variables. And I can say that x bar is normally distributed because they say here that the population is normal, and that's where this theorem kicks in. If the population is normal, then x bar is also normal. So x bar is normally distributed because the population is normal. Oops. And at that point we've answered the main question, what is the distribution of the sample mean? We've said what kind it is. It's a normal distribution. But when they ask you to figure out the distribution, they want you to say which specific normal distribution it is. So I need to say x bar is normally distributed with, and then state the mean of the x bars, and also state the standard deviation of the x bars. So we know according to this theorem that the mean of the x bars will always be the same as mu, and mu was 195. So I can say the mean of the x bars is 195. And the standard deviation of the x bars would always be sigma over root n, and we know that sigma is 3152, and we know that n is 24. And if we put that in the calculator, we can get an approximation for that standard deviation. So we have 31.52 divided by the square root of 24 is approximately 6.43. Let's see, we have 39 but followed by a 9, so that 39 would round up to a 40. So when you're answering questions about the distribution of x bar, it's important that you get four things occurring there. One is what kind of distribution is it? It's normally distributed. The second is how do you know? Because the population is normal. And then narrow it down to a single normal distribution by giving the mean and the standard deviation. Numbering those steps isn't something that you have to do, but it's something you should at least mentally tick through to make sure that you've gotten all four of those questions answered. Now let's see how we can use that information. For a sample of size 24, determine the probability that x bar is between 190 and 200. Well, they just told us that, or we just figured out that x bar is normally distributed, so the way I would do a probability question about something that is normally distributed is using area under a normal curve. So I would put the mean of the x bars in the middle because that is our variable, and the mean of the x bars is 195. And then I'd put the two boundaries, 190 and 200 on the picture. And the probability of x bar being in between those is the same as the area in between them. And this time drawing that picture is justified because I know x bar is normally distributed. I would go on to the z-scores. The first z-score, 190, minus the mean of 195, divided by the standard deviation of x bar, not the standard deviation of the population, but the standard deviation of x bar, because this is a probability question about x bar. So divided by 6.4340, and let's see what that is. So we have 190 minus 195 divided by 6.4340, and I get a lucky looking z-score of negative 0.777. And the other z-score would be almost the same, just positive. And I can say that these are going to be equal and opposite anytime these two numbers that are my boundaries are the same distance away from 195. So since I'm going 5 in each direction, I know these are going to be equal but opposite numbers. And then we can finish that off by doing the normal CDF to figure out that area. So normal CDF from negative 0.777 to positive 0.777 would be that probability. And just thinking about that before I go to the calculator, the empirical rule says if I went from negative 1 to 1, it'd be about 68%. This is less distance out, so it would be smaller than 68. We know from previous work in Chapter 6 that the quartile z-scores are 0.674 and negative 0.674, and going in between those would give 50%. So this should be bigger than that 50%, smaller than the 68%. Let's see what the calculator says. So normal CDF from negative 0.777 to positive 0.777 gives a number in between 50 and 68, like I expected, 0.5628. And so there's my answer. And so a few good things. One, that was the size number I was expecting. Two, I was able to use a bell-shaped curve because I know that x bar is normally distributed because of the fact that the population was normal and based off of Theorem 7.4. The bad news, however, is if we put the hypothetical on that the reason we wanted to land between 190 and 200 was so that we could be within 5 units of the correct answer and get paid, then this is not a very good probability of getting paid. And if I was unhappy with the chance of landing in this range and I wanted to have a better chance of landing in there, a good strategy to fix that would be to up the sample size. And if you look down here, you see that's the very next thing that happens, is they say, let's look at this all again with n equals 84. But just a quick thought of like, why would we want to look at it again? Why would we want to up our sample size? Because if it was important for us to land between 190 and 200, a 56.28% chance of that isn't very good. So if n is equal to 84, that's not going to affect the type of distribution. It's still going to be normal because the population is normal. But what it will affect is the standard deviation of the x bars, because now that would be the original sigma, which if we go up and look at that, the original sigma is 3152. So 3152 divided by the square root of this new sample size of 84, let's see what that gives for the standard deviation. So I would have 31.52 divided by the square root of 84, and my standard deviation now is 3.4391. So how does that affect the answer to this question of what's the distribution? What's the distribution of the sample means, x bar? I'm still going to say x bar is normally distributed because we were saying that because the population is normal, so it's still the same reason. But now when I give the details, the mean of the x bars is still the same, 195, but the standard deviation of the x bars, sigma x bar, is approximately 3.4391. So when you change the sample size here, since the population still remains normal, x bar is still normal, but we get a different standard deviation. And what we want to do is turn the page and see how that affects our probability of landing in this zone where we would get paid because we're within an acceptable distance of the right answer. So we'll look at that on the next page. So continuing on, now that we have that sample of size 84, determine the probability that x bar would be between 190 and 200. You would think that upping your sample size would produce less error and a better chance of getting paid, but let's verify that. I'm going to draw the bell-shaped curve for this because we just said that x bar is bell-shaped on the previous part, and in the center we had a mean of 195. We're still looking between the boundaries of 200 and 190, so whatever this area is will still be our probability. And in fact, when you look at the picture, it looks like the same picture. You'd expect maybe you'd get the same answer, but that's not true, because now that we have a different sample size, we have a different standard deviation. So when I do my z-score, the first one, it's still 190 minus 195, but when I go to divide, I'm dividing by the standard deviation of x bar for a sample size of 84, and we just computed that, and it was 3.4391, so that's the number that we use this time, which is different than the previous one where we divided by the 6.434. That was because our sample size was 84. So when you're going to do your z-score, not only do you have to consider that you use the standard deviation of x bar, but you have to make sure it's for the right sample size. Alright, so let's see what we get for that. So for our z-score numerator, we would want 190 minus 195, always in parentheses for that numerator on z-scores, and divided by 3.4391, and I get a z-score of negative 1.456. Z2 is the same distance out, but opposite direction, so that would be positive 1.454. Let me bring the calculator back in here for a minute. Not sure why I said a 6. That was a 3 followed by an 8, so we'd round that up to a 4. Negative 1.454. And now let's go ahead and do that area. That area, which is also the probability, would come from normal CDF, our left z-score, negative 1.454, to our right z-score, positive 1.454. And put that in the calculator and we'll know our area. So distribution, normal CDF, negative 1.454 to positive 1.454. And now we have 0.8541, a 0 but followed by a 5, so we'd round that up. Alright, so just kind of a quick summary of what's going on there. We said that if you were to use a sample of size 24, and if you thought of the hypothetical situation where you're getting paid if you land within 5 units of 195, the chance of landing in that distance and getting paid is 56.28%, which is not that good. But if you up the sample size, that'll decrease the standard deviation. We didn't show it in the picture, but that means this picture is actually narrower and therefore taller, and the boundaries stay put. So if your curve gets narrower and taller while the boundaries stay in the same place, you're going to have a higher chance of landing in between those. And we see that because the z-scores become bigger, and we get this bigger area, better chance of getting paid, about 85%. Alright. And then the final question is, if you went back to the HD TV question from the previous section, does this theorem 7.4 allow us to determine that probability that we were kind of stuck on before, that x bar is between 1182 and 1382? And unfortunately we have to say no, because the population was unknown. And in order to use Theorem 7.4, you have to know that you have a normal population, and that problem didn't state what the population was. And worse yet, that problem is about the price of HD TVs, and most things that are about money tend to be right skewed, because most people will buy the cheaper TV, and only a few people, maybe the wealthiest people, would buy the most expensive ones. So a lot of times money things end up being right skewed, and in order to use Theorem 7.4 we'd need a population that was normal. At best our population was unknown in that problem. At worst it might have been right skewed, maybe even severely right skewed. So we need a way out of this situation because we want to be able to do problems that involve money, and Theorem 7.4 is a lot of times not going to work there, and that's where Theorem 7.5 kicks in, so we'll look at that next.